Yeah. All right, hey Hallie. We are on the top of like part 2 of 3-2. And I had them put this in the corner because I think you have to know this stuff for like number 4 on your homework assignment maybe. But we talked about sample and population, like what symbols they use for like population mean and sample mean, right? We talked about X bar. X bar is what you use for a sample mean, but population mean is this guy. He's like written like this, right? He kind of looks like a cursive M maybe, but like pointy. He's pronounced mu is what he's pronounced, right? And then variance and standard deviation. Standard deviation is S for a sample, but he is sigma for a population, okay? And then variance is the standard deviation squared, so he's just S squared or sigma squared, okay? And so those are the symbols that you will use for those guys, okay? Population, sample, mean, variance, standard deviation. We'll use those tons and tons and tons going forward. Got it? Okay, let's go down to part 2, and this is something that you will use a lot. In fact, I will give you a laminated copy of this bell curve, or this thing. This is called the empirical rule. It's also listed down here, but I'm going to rewrite it. Empirical rule, okay? So here's what happened. Here's how this empirical rule chart was generated, right? Okay? Some old dead guy, I don't even know what his name was, maybe empirical, I don't know. That's why it's named that. I don't know. Some old dead guy crunched a bunch of tables, right? He took like thousands and thousands and thousands of data points for different things like height and weight and things that should be normally distributed. What's normally distributed mean?
A bell curve.
Like a bell curve looking thing, right? Okay, so where the highest frequency is in the middle, like on the average, right? Okay. So he crunched a bunch of numbers and he came up with this scale that basically said, out of all of the data sets, like thousands of data sets that he analyzed, if I take the average, right? The average is right here in the middle, and I add 1 unit of standard deviation, whatever the standard deviation is, and I subtract 1 unit of standard deviation, about 68% of the data should live within 1 standard deviation of the mean, right? Okay, then he said, okay, if I go 2 standard deviations, if I add it again and subtract it again, about what percent of the data should live in there? 95% of the data should live within 2 standard deviations of the mean, right? And then we have 3 standard deviations. If I add it again and subtract it again, about 99.7% of people should live in that range, right? Okay. So let's maybe equate this to my scores that I have over here. Let's say that the average on a test was an 85. Write this down off to the side. We're going to create our own stuff here.
Abraham de Moivre.
What?
That's the guy that created it.
Okay, sure.
Okay.
Abraham Lincoln.
De Moivre.
Oh.
Yeah. Okay.
Moivre.
Okay. And let's say the standard deviation is 5.
I don't know.
Okay. Standard deviation is 5. So I'm going to draw I'm going to make like a little chart here. What goes in the middle of my chart? 85. That's the average, right? That's the X bar. That's the average, okay? Then I'm going to add 5 and I'm going to subtract 5. And that range is what? No, just wait. That is what range? 80 to 90. Shh, listen. And 68% of people should live there, right? Okay. Now if I do it again and I go 5 units more, that would be from what to what? 75 to 95. About what percent of people live there? 95% of people are going to be in that range, right? And then if I go 1 more, that would be from a 70. Whoa, let me go green. 70 to 100%, right? And that's that range. That's adding another and subtracting another. And about 99.7% of people are going to live there. That means 0.3%, not even 1% of people live outside of that range, right? So 0.3% of the people either scored a higher than 100, maybe they got a bonus point, right? Or lower than a 70, according to this data. Yeah?
How do you figure out the percentages?
They give it to you.
Oh.
He crunched the numbers and he said that if it's normally distributed, approximately 68%, approximately 95%, approximately 99.7% of the data should live in that range. Yeah. Now, given that, and given that it's a bell curve, let's say I have my 85 here and 90 here, okay? And this would be an 80, right? We know that 68% of the data lives in this little bubble right here. But what percent of people are scored just between an 85 and a 90? 34%, half of 68. It comes out to be a little bit more than 34%, 34.13%, but 34% is going to be between those 2 points, right? Okay, and then I could do the same thing for how many people scored between a 90 and a 95. About 13.5%, right? That's what that boils down to, okay? How many people or what percent of people scored higher than 100? 0.13%, right? So he has this blocked off. Again, this is by studying thousands and thousands and thousands of data sets. He figured out how many actual values lived in that range, okay? And did data set after data set to figure out about how much was like in that range according to the standard deviation and the average, right? And he came up with this table, okay? All right, so let's go to an example. IQ scores have a bell-shaped distribution with a mean of 100. That means X bar is 100, okay? And a standard deviation of 15. I'm going to write that off to the side. So there is that, okay? 100, standard deviation of 15. So I'm going to put my 100 in the middle and standard deviation of 15. If I add and subtract, that first mark will go from what to what? 85 to 115, okay? My second mark, if I add and subtract again, will go from 70 to 130. Yeah. If I add and subtract again, it will go from 55 to 145. If I add and subtract, I'm adding and subtracting 15, right? Okay. They want to know what percentage of IQ scores are between 70 and 130. Okay, 70 is right here, and 130 is right here. That is from -2 to +2. Does that make sense? 2 standard deviations below to 2 standard deviations above. 2 standard deviations below to 2 standard deviations above. How much percent is within that? 95%. Do you see how that works? 95% are going to live between 70 and a 130.
We have to go 3 instead of 2 now.
What?
Yesterday we just.
Oh, yes. Okay, so yes. I'm glad you said that. So you remember yesterday where I said everything that is without, like outside of 2 standard deviations is considered rare, right? Or like a significantly low or significantly high value. Because what percent lives within 2? 95, right? So only 5% of people are living on the outside. That's pretty small percentage, right? A very small percent. Not impossible for you to live outside here, but if you do, you are in the highest 5% or lowest 5%. Actually, you're in the highest 2.5% or the lowest 2.5%. That's why we use 2 as our cut marks for what's considered high and low, right? Okay. Now you could go even more standard deviations than that, but it's going to end up being lower than 0.13% is beyond that, right? Makes sense? Okay. So within 2, anything outside of 2 is considered a really low number or a really high number, right? But they even cut it down even further. 99.7 are going to live within 3. So there's only 0.3% that lives outside of 3, right? Okay, like actually 0.15 and 0.15, right? Okay, does that make sense? Okay, so yes, I get that. Like yesterday I was telling you, but that was for like what's considered low and what's considered high. Okay, now it's actually giving you what percent does that equate to. Got it? Okay. All right. Now some other old dead guy. And his last name. You want to try to pronounce that? Chebyshev's. Chebyshev's. Yep. Chebyshev's theorem. Right. And his theorem said this, okay? He came up with his own set, right? And he's like, I don't believe that this is quite true. I'm going to come up with a formula for it, to figure out how many people live outside of it. But this formula only works for numbers greater than 1, right? So if I'm talking like how many standard deviations, I have to be doing at least 2 standard deviations and not just 1 standard deviation. So here's how this works. For K2 and K3, we get the following statements. So here's what he says. If X bar lives here, and 1 standard deviation is here, and 1 standard deviation is here. So this would be like +1s and -1s, okay? 2 standard deviations, so +2s and -2s. He has a formula for figuring out what percent lives in that range, and it is this. It is 1 - 1 over k squared. That will give you the percent that lives in that range, right? So if we are doing 2 standard deviations, right? 1 over 2 squared, this would be 1/4. What is 1 minus 1/4? 3/4, which would be what percent? 75%, he says, live within 2 standard deviations. Now, what percent should live within 2 standard deviations if you look at the above rule? 95. That's a pretty big discrepancy, right? This old dead guy said 95%. This old dead guy said 75%. Whatever. Okay? We will use the empirical rule most often, but I think you have a homework assignment on this, all right? Let's say we're going 3 standard deviations. So plus 3s and minus 3s, right? And we've got this little loop-de-doo right here, right? We go 1 minus 1 over k squared. What's k in this case? 3. 3 squared is 9. What's 1 minus 1/9? 8 over 9. What's 8 over 9 as a decimal or percent? 0.8 repeating, right? Or 0.889 or 89%. So he says that 89% should live in this range. What percent should live in the range? 99.7%. Okay, so a little bit of discrepancy there. All right, so let's look at what they have here. They say, so right here, it says at least 75% should live within 2 standard deviations. At least 89% should live within 3 standard deviations. If your IQ scores have a mean of 100 and a standard deviation of 15, again, we have 115, 130, 145. We've got 85, we've got 70, and we've got 55, right? What can we conclude from Chebyshev's theorem about, let's go the same numbers. Let's say 70 to 130, because that's what we were doing the last time. 75%. Okay, that's for Chebyshev's theorem. Okay, it was 95% for the empirical rule. Okay, good. And one is saying one and one is saying the other. Okay, and we don't know which one is right, except the empirical rule is more widely accepted to be the correct one. But Chebyshev's is one nice formula for all of the standard deviations, right? Okay, so it's at least got one formula for it. So they both crunched numbers. They came up with their own set, and they said, no, it should be closer to this. No, it should be closer to that, right? Okay, there is how that works. Got it, got it? They're just conflicting results. Whatever. We will more widely use this one. I'll give you a laminated copy of him. In fact, I might have him now. You do? You do? Yeah, you have one. I will give you a laminated one, though. Yeah. He is, where is he at? Right after section 3.2. So if you want a big one, it's right after section 3.2. There's a big one for it. Yeah. There is stuff on the back, too. The one thing that's on the back, the chart that's on the back, I think, has to do with your correlation coefficient. R, like what's considered a good R and a bad R, which I think is what we did in chapter 2. So I don't know why that's on there. I don't know. Anyway, so there's that. Okay. He is, yeah, I'll show you right here. I'll give you a laminated copy of one of those. Okay. All right, one more thing really fast. And this is a little bit more involved, so buckle up. Ready? One more thing. One more thing. Okay. I want to, let's say, this is something called the coefficient of variation, or CV. Coefficient of variation. Everybody say coefficient of variation. Coefficient of variation. All right, here's the deal. I want to be able to compare two things that should not be compared. Like, let's say I'm doing ACT score versus SAT score. I want to be able to compare them. But the problem is, they are not on the same scale. True? So what I do is I convert both of them to a score, and then I can compare them. What's that?
Next week for the MTSS conference.
Thursday, Friday, right?
Are you staying home or are you gonna go?
I'll probably stay home and
April know to get you something.
yeah. But I'll drive back and forth, you mean? Or are they doing it Zoom?
They have Zoom and in person. So
Oh.
the elementary staff's gonna go in person.
Oh.
I'm staying here.
You are staying here?
Mr. Rubin, Mr. Linescu will be gone those 2 days.
Gotcha. Okay, I had thought about maybe just driving back and forth, but who's going from the high school in? Is anybody going?
Mrs. Fritz, you and Mrs. Cleaver.
Like, is anybody going though, or are they all doing Zoom?
Maybe Mrs. Fritz if she goes.
Right.
So I gotta call her. So
Okay.
it might just be-
I think she got out yesterday. Okay. If anybody else goes, I don't mind going, but I'll probably drive back and forth because my husband.
Mrs. Cleaver has a cross country meet Thursday, so
Oh.
I don't know what time they leave. Where's it at next Thursday?
Google Junction,
So you'll leave at like what, 1?
3 to 11.
Okay.
I'll just tell her to find you a sub.
Sure. Yeah. That sounds good. Okay.
Mr. Johnson,
Yes.
can he teach?
Yes.
Can he teach the stuff?
Yes.
Mr.
So every time I have him as a sub, I leave him an extra copy of everything that we're doing, and he fills it out and makes it like an answer key.
Yeah.
So I don't know if like the kids ever ask questions, but like he could help them if you.
Hardly.
Yeah. Yeah.
You like-
So yeah. So anyway.
Bud, get married.
Yeah, I'm not good.
Okay, so let's do this. Somebody real quick, look up what the average ACT score and the average SAT score is. Go.
19 in Nebraska.
What those?
No.
19?
Nebraska or in the United States?
I don't care.
SAT.
Whichever.
Hey, what's the difference between the two?
SAT is used on code.
SAT is usually used on the coasts.
Yeah.
They generally widely accept the SAT score. SAT score is in the is in the hundreds,
It's
like
like 1600.
2100 or 1600 or whatever it is, right?
1600.
Is the average?
I think that's highest.
Oh, 1600 is
ACT
highest.
national is 19.4.
Okay, 19.4. Put this down in the corner. With this, oh, what's the standard deviation for ACT score?
Are you calculating that while I figure
Thank
out
you.
SAT?
Sure.
Okay.
Look up mean and standard deviation for SAT score.
But like, you probably won't get a, you probably won't do it.
Can you just find the estimated standard deviation?
19.4 with a standard deviation of 5.7.
And what does the standard deviation mean? That's like.
Like how much it deviates.
Standard.
It's gonna be
Oh.
small, probably.
Oh, okay.
Makes sense, right?
I was thinking average for some reason. I'm like, how is it?
The mean, they give me a range for the mean.
Well, that's what they gave me, yeah. For SAT, it says.
They said between
around
1024 and 1028. So should we go the average?
1020.
Let's go 1026 for the average SAT score with a standard deviation of 216 or 217. Okay, now here's the deal. Here's what I want to be able to do. I want to be able to compare ACT and SAT score. So if I took the test, and let's say on the ACT test, I'm going to put my X value. I'm going to say my X value is a 24. Let's say I scored a 24 on the ACT. And let's say on the SAT, I scored a 1500. Oh, no. Which one is better?
The 15.
Probably the 15.
You think the 1500 is better?
Yeah.
Think so?
The top is 1600 for SAT.
Yeah, it's more than 2 standard deviations.
Okay, let's go. Let's go. Pull them down a little bit. Let's pull them down a little bit. Let's go 1300. Sure. Okay, write this down. Put this down over here in the bottom corner. I want to be able to compare. I want to say which one is better, ACT score or SAT score, given that I've taken both. Did I score better on the ACT or did I score better on the SAT? And the problem is I can't compare them because obviously 1300 is higher than 24, but they're not on the same scale, true? Okay, so what we're going to do is something called the coefficient of variation, right? Okay, coefficient of variation is going to convert both of them to the same units, okay? And so to do this, the formula for CV is X, wait a second, let me look, is
S over X times 100.
S divided by X bar,
Is it X bar?
Yeah.
You're right.
X bar times 100, okay? S over X bar times 100. S over X bar times 100.
That makes sense.
Okay? Yeah. Yeah. So do I want to use my average probably?
For what?
Or X bar,
Yeah. I want to use my average.
so not necessarily X.
So not this one and not this one. Okay? I want to use my value. My average was a 24 on the ACT. My composite average on the 20 was a 24 on the ACT. So to calculate the coefficient of variation, I want to do S, which was 5.7 divided by 24, and I'm going to take that times 100.
Oh yeah, because you have no.
23.75.
What?
How
23.75.
how's that gonna tell you if it's good or not? Because you don't have a base.
You don't have
mean.
the average in there.
Yeah. So you don't know if you're above average.
It doesn't matter. It doesn't matter. It goes by the standard deviation.
Yeah.
Yeah. Oh,
The deviation for
hold
what,
on.
though?
For
Standard
sets of
deviation
non-negative
is
expressed as
average.
percentages described as standard deviation relative. Compare the variation. Oh, compare the variation. Okay, hold on. Just wait a second. Let's do it.
The ACT
Do
score is better.
217 over 130.
13.
Or 1300, I mean.
No.
16.69.
16.69 if you take it times 100.
ACT.
Now, here's the deal, okay? This is not telling me, I should rephrase. This is not telling me which one I did better on. This one is telling me how much further I did away from the average. Like this one I had more variation. More variation,
And that's percent, yeah.
okay? More variation relative to SAT. Does that make sense? Not necessarily that I did better. If I want to know which one I do better on, I'm going to convert them to what's called a Z-score, which we'll do like maybe at the end of this chapter. I don't know, right? So I had more variation in the ACT score than I did in the SAT score, even though the scores were lower, right? Okay, so more variation there. All right, so here we go. Verizon data speeds and earthquake magnitudes. They have two things going on. Data speed, and earthquakes. Okay, here's the two things that we're comparing, and I want to know which one has more variation. So which one is like less reliable, basically, or like more variable. Okay, Verizon data speed is 17.6 for an average with a standard deviation of 16.02. And earthquakes had a magnitude of 2.572 with a standard deviation of 0.651. Now here's the deal. It looks to me as though Verizon data speeds had more variation because a 16 for a standard deviation is way bigger than a 0.6 for a variation, right? Like these numbers are all over the place. But the problem is the average was a 17 to begin with, right? It's way higher than this guy's average. So which one actually varies more? We're going to figure this out. So coefficient of variation is S divided by X bar times 100. That's all you have to do. S is 1602 divided by 17.6 times 100. What do you get for that one?
91.02.
91.02 is what he is, okay? That is his variability, 91.02 like percent basically. This guy, if I take S 0.651 divided by 2.572, and I take him times 100, what's his variability? It's going to be less than 91. 25.28. Okay? So, data speeds had a 16 for a standard deviation. It looks like it varies more. And relative to earthquakes, it does in fact vary more, right? Because 91 as a variability is way bigger than a 25 as a variability. Does that make sense? So, data speeds are less consistent. Earthquakes, usually all of them are about like small earthquakes, right? Every once in a while you'll get one in there that's maybe like a 6, right? A 6 earthquake is like pretty serious.
No, it's
Do you know what I'm talking about?
6 or a 7.
Shut up.
Whatever. Okay? Like a 6 earthquake might do a little bit of damage, but like a 3 earthquake, you might be able to feel it, but it's not going to do as much damage, right? Okay? So earthquakes, most of the time you're getting like all about the same amount of earthquakes. Data speeds, sometimes you're getting really slow data, sometimes you're getting really fast data, okay? So this one has more variability. More variability.
Variability.
And this one is more consistent. Does that make sense? Okay, more consistent, more variability. Compare the data speeds to variation among earthquake magnitudes. Data speeds is more variable. Earthquakes are more consistent. Yeah? Make sense? Okay, that's what we're comparing.
So on the whole.
There is that. So that homework problem is going to be like number 41.
Why did you text me this morning?
No, it's number 22.
No, it's not. It's number 22.
Can we do
On
it together?
22, do we cross out the last 5?
Now, number 22, here's what I want to do.
Just do it together.
I'm going to show you how to calculate standard deviation using your device.
I was just trying to make sure you know.
What?
Using your device. X bar and S. And X bar and S. Those are the two things that we need for both of these data sets. Okay, what calculators do you have? Get them out. Let me see them.
Texas Instrument.
You got one of those.
Texas Instruments 56 probably or something.
I got the same one
Emily
as
has
Delaney.
the same
I
one.
have the same as.
Anybody have the fancy big ones? Who has my fancy big
I
ones?
ain't rich.
Well,
These ones are
but
graphing
some of them are in
calculators.
calculus. You're in calculus, yeah.
I don't
Okay,
like this
so
one.
you
I
should-
never use the graphing calculator.
You should, because that one I know how to do on.
No,
All
these
right.
don't get useful.
Okay, I'm going to shut this video off. Hallie, I'll show you how to use your calculator tomorrow with number 22. Okay, I'll show you how to do that. We'll get your calculator out because every one of them is different. Okay, but there's that.
You racist? You racist?